Microbacterium tuberculosis is the etiological agent of tuberculosis. Tuberculosis is one of the top 10 causes of death and the leading cause of death from a single infectious agent. Only in 2018, there were 10 million new cases over the world. 1.5 million people died, and WHO estimates that there were around half a million new resistant cases, mostly to rifampicin. Rifampicin is the most effective first-line drug. Multi-drug resistance TB is a public health crisis and an active field of research. Existing models for predicting drug resistance from whole genome sequencing data generally falls into two classes. The first one, which we refer to as catalog models, involve the testing the whole genome sequencing data of an isolate for the presence of a point mutation associated with a known drug resistance. If one or more such mutation is identified, the isolate is declared to be resistant. The methods in this class are easy to understand but not very accurate, especially in identifying novel drug resistance mechanism or screening resistance to untested or rarely used drug. The second class, which we will refer to as a machine learning methods, mostly uses complex black box machine learning models for prediction. Such methods tend to result in highly accurate prediction at the cost of flexibility and interpretability. The problem with these methods, the methods in this class, is they would not provide much insight into a drug resistant mechanism. In this research, we propose an interpretable model with comparable accuracy to commonly used machine learning models. The proposed method train a rule-based model for classification. To train a such classifier, our method utilizes group testing and Boolean compressed sensing. Group testing arose during World War II when the United States was recruiting individuals for military and they needed to be tested for syphilis. Since the number of infected individuals were low and the process was costly, Dorfman suggested that they can pool blood samples into specific groups and test the groups instead of individuals. With this setting, a negative result for a group would imply no infected member in that group, and the positive result for the group would imply the presence of at least one infected member. The group testing can be represented by a Boolean matrix A, where each row represents a group or a pool, and each column represents an individual. The element I and j of this matrix would be equal to 1 if the blood sample of person j be in group I, and it would be equal to 0 otherwise. Now assume that we tested all groups and represent the results with vector y. Then we can show our group testing as a Boolean product of matrix A times vector binary vector W, where Wj representing the infection status of the jth individual. The group testing, or that Boolean product that we showed in the previous slide, can be presented as an optimization problem where L naught of W is the number of non-zero entries in the vector W. The solution of this optimization problem indicates which individual is infected. This is a non-convex and non-linear problem which is known to be NP-hard, but we will talk about solving this problem in the future slides. For now, we want to show how we can use the concept of group testing for creating an interpretable binary classifiers. The idea of group testing can be extended for creating rule-based classifier. In general setting, a context-specific technique for dichotomizing features and converting feature matrix to Boolean feature matrix may be needed. However, in our case, in the case of drug-resistant prediction, our features are already Boolean, and there are presence or absence of the specific single nucleotide polymorphisms or SNPs, and therefore there is not such conversions needed. The feature matrix that we have in our problem is already in the Boolean form. Now assume that X is a feature space and the set of 0 and 1 is our label space. The classifier C hat can be defined as this Boolean product. Furthermore, this Boolean product can be expressed as a rule-based binary classifier. Now let's take a look at an example. In this example, we have a Boolean feature matrix with 8 features, and this is our label vector. The solution of this optimization problem is equal to vector W, where the first element and the 7th element are equal to 1, and other elements are equal to 0. We can see that we can form this Boolean product to a rule-based classifier such that this one, for example, here we have if feature 1 is true or feature 7 is true, then predict the label is true. You can see that when the feature 1 is true, the label is true, and when feature 7 is true, the label is also true. We don't have such relation between labels and the features for all our features in this problem. Now that we went through the idea of group testing and how we can extend this idea to train an interpretable or rule-based binary classifier, let's see how we can use this idea for predicting drug resistance. Our process contains the following steps. First, we combine the data from Patrick and ResectTB databases to obtain 8,000 isolates together with their resistant susceptible status or labels here. These labels for 7 drugs, including 5 first-line drugs and 2 second-line drugs. After pre-processing the data and processing the whole genome sequencing data for these 8,000 isolates, we then extract single nucleotide polymorphisms or SNPs for each isolates. In the second step, we created binary feature matrix where each row represents an isolate and each column indicates the presence or absence of specific SNPs in that isolate. Then, for each drug, we produce a vector Y as the label vector and form the group testing problem for each drug. At this stage, in order to produce a binary classifier, we needed to solve the sparse vector recovery problem. However, as we mentioned in the previous slides, this is a non-convex, non-linear problem, which is known to be NP-hard. To solve this problem, inspired by Molotov and Varshin technique, we changed the Boolean compressed sensing problem to an integer linear programming. To do so, we relaxed the L0 norm in the objective function to L1 norm, and we replaced the nonlinear Boolean product here to 2 closely related linear constraints. We also added the slack variables and regularization to provide a trade-off between the sparsity of disjunctive rule and the total slack. Note that even though the total slack corresponds to training error, it's not exactly equal to the training error. And these conditions is not ideal for machine learning tasks because first, we cannot accurately calculate the training error, and second, it is not possible to assign different weights to different components of the error. Note that assigning different weights to different components of error could be really helpful when we are dealing with highly unbalanced data or when we are in the situation when the cost of the false positive is different from the cost of the false negative. Again, to add this flexibility to our model, we divided the regularization coefficient and total slag to two components, and we changed the constraints for the zero set from continuous slag variable to binary, and we replaced the equality in these constraints to two inequalities. Note that the first inequality makes sure that when this product is equal to 0, the slack variable is equal to 0. And the second equality makes sure that when this product is not equal to 0, the slack variable is equal to 1. Now note that in this new formulation, the lambda p and the lambda z controls the trade-off between the false positives and false negatives and jointly influence the sparsity of the rule. This formulation can be further tailored to optimize a specific evaluation matrix since we have the false positive and false negatives in the objective function. Okay, finally, we can explain our drug resistance prediction pipeline in three simple steps. First, we are going to collect the data about the isolates and their labels. Then we're going to extract the SNPs for each of those isolates, and we are going to create a feature matrix based on them. In this feature matrix, each row represents an isolate and each column represents a SNP, and each element would represent the presence or absence of that SNPs in that isolate. Then we are going to feed that feature matrix to our integer linear programming problem, and we are going to extract the rule-based classifier that we want. Note that since we have the trade-off between false positive and false negative and the sparsity of the rule-based model that we want, we can produce the desired classifier based on those hyperparameters. So now let's see how our model actually works. Evaluating the performance of an interpretable predictive model can be really challenging. While the most evaluation methods focus on the predictive accuracy, it's really essential to assess the model's interpretability. And even though there is no unique definition for interpretability, the predictive descriptive relevant framework introduced by Murdoch et al. Actually captured the essence of what we want to do here. We adapt their model, we adapt the concept that they're introduced, and we defined our predictive accuracy, descriptive accuracy, and relevance as follows. For the predictive, it's really straightforward. It's similar to machine learning models. We calculate the area under the curve of ROC curve for our model and compare that to the commonly used machine learning models like random forest and L1 logistic regression. We use this metric to show that our model actually produces classifiers that are comparable, the result of them are comparable with the commonly used machine learning models. As you can see here, our model is the accuracy of our model is slightly less than logistic regression, in all the drugs, but it's really comparable with the accuracy of random forest, and in some cases are higher than random forest, in some cases are slightly lower than that. For descriptive accuracy, we define the descriptive accuracy as the simplicity of our model. By that we mean our model has a high descriptive accuracy if it can be simple and it can describe the insight behind the prediction to human users. To calculate the descriptive accuracy of our model, or to show that the high descriptive accuracy of our model, we compared the area under the ROC curve produced by our method for different sparsity of rules or rule sizes. This comparison between the method and different parameter values help us to evaluate its ability to produce a simple model with high accuracy or high AU ROC curve. Note that the simpler model they're easier to understand for human users. And in this paper, again, we defined the descriptiveness of a model by its simplicity. So, as you can see here, we calculate the AUC of ROC curve for all the drugs for different rule sizes. And you can see that our model can produce classifiers even with a small number of SNPs or a small size of rules, which has acceptable accuracy in terms of AU of ROC curve. To find out how relevant our classifiers are and how they can be helpful to their user, we assess the relevance of the model produced by our method by observing the fraction of SNPs used by the model that are located in genes previously reported to be associated with drug resistance. In this plot, you can see that when we put the upper bound for the number of SNPs that is allowed our classifier to have, we have a significant number of SNPs that previously known to be within the genes that are associated with drug resistance. To show how well our model can detect those SNPs, we are comparing the results of our model to logistic regression. If you remember, we showed that the logistic regression do a better job when we compare the accuracy of ROC curve of logistic regression to our approach. But in this plot, you can see that our approach can detect more important SNPs than logistic regression, the SNPs that we already know that they correspond to drug resistance. Thank you.